So in this lesson, we'll be discussing the concavity of a function f and how that concavity is related to both the first and the second derivative. So we use concavity to describe the curvature of a graph. So when we say something's concave up or concave upward, we're saying that the graph is curved up. And when we say it's concave down or concave downward, then we're saying that the graph is curved downward. So if f is a differentiable function on some open interval I, then we say that the graph of f is concave upward on that interval if the derivative of f is increasing on that interval. And we say that the graph of f is concave downward on that interval if the derivative of f is decreasing on that interval. Now that might seem kind of weird to think of the first derivative instead of the function itself. But remember what the first derivative represents. The first derivative represents the instantaneous rate of change, or the slope of the tangent line to a point. So let's start with this first piece that is curved upwards, concave up. And what I'm going to do is I'm just going to pick, we'll do 0. I'm going to pick a few points on that graph. Now, if I look here at this point, we would say that the derivative is 0. We have that horizontal tangent line. As my x values increase, so does the slope of the tangent lines at those points. So as we can see on this side, our slopes are getting larger, which means that the slope, the derivative, is increasing. But if we look at the negative side over here, the values that have slopes that are negative, here we have a steeper tangent line than here, which means that this slope has a larger negative number than this slope. And if we think about how negative numbers work, then that means that as our values become less negative or move closer to 0, they're actually increasing. So we might think of this as having like a slope of about -2. We might think of this as having a slope of about -1, and then 0, and then a slope of 1 and a slope of 2. So even though our lines are becoming less steep to this side of that minimum value, the slope values, the derivatives themselves, are actually increasing because they are becoming closer to 0. Likewise, if we look over here on our segment that is concave down and we pick a few points, then here at our maximum, we would have a horizontal tangent line. So here our derivative would be equal to about 0. On this side, to the left of that maximum value, we would have positive slopes, and we can see that as we are approaching this place where the derivative is 0, our lines are becoming less steep. So we might have something like a slope of 2, and then a slope of 1, and then a slope of 0. Then afterwards, our slopes are negative and are becoming steeper. So we might have, for example, this might be a slope of -1. This one might be a slope of, say, -2. And so if we think about it, we're going from -2 to 1 to 0 to -1 to -2. Here, our derivatives are, in fact, decreasing. So if we want to know where our graph is concave up or concave down, what we need to know is where is the derivative increasing and where is the derivative decreasing. And from our previous lesson, we know that we can tell where something is increasing or decreasing based on its derivative. But in this case, what we're wanting to know, if it's increasing or decreasing, is the derivative. So to know where the derivative of f is increasing, we need to know where its derivative is positive. And the derivative of that first derivative will be the second derivative. So if the derivative of the first derivative, if the second derivative is positive, we know that the derivative is increasing, and therefore the graph is concave up. Likewise, if the derivative of the derivative, the second derivative, is negative, we know that the derivative is decreasing, and therefore the graph is concave down. And that's what we use to test for concavity. We look at the second derivative. So let f be a function whose second derivative exists on an open interval I. If the second derivative is positive, is greater than 0 for all of the x values in that interval, then the graph of f is concave up on that interval. Because if the second derivative is positive, then the first derivative is increasing. And likewise, if the second derivative is less than 0, if the second derivative is negative, then we know that our first derivative must be decreasing. So if the second derivative is less than 0 for all x in an interval, then the graph of f will be concave down in that interval. So in this next example, we want to know for what open intervals is the function concave up and concave down. And so to check for that, we're going to look at the sign of the second derivative. If the second derivative is positive, the graph is concave up. If the second derivative is negative, then the graph is concave down. So I need to start by finding the second derivative, which will be the derivative of the first derivative. To find the first derivative before I get started, I'm going to rewrite this as 6 times x squared plus 3 to the negative 1. You don't have to rewrite it this way, but I think that writing it this way and bypassing the quotient rule here makes finding the first derivative just a little bit easier. So then the first derivative will be equal to negative 6 times x squared plus 3 to the power of negative 2. And then we have to take the derivative of the inside there. We've got to complete the chain rule. The derivative of x squared plus 3 will be 2x. So we would have negative 6 times 2x gives us negative 12x. And we can move this down to the denominator if we want. So that's our first derivative. And if we wanted to, we could use the first derivative to find the critical numbers and then to figure out where our function is increasing or decreasing. Since they haven't asked us for that information, we can kind of go ahead and move to the next part, which is finding the second derivative. So to find the second derivative, I need to take the derivative of the first derivative. And to do that, this time I am going to go ahead and use quotient rule. So the derivative is going to be low. The bottom is x squared plus 3 squared times the derivative of the top is negative 12. So low d high minus high, negative 12x, times the derivative of the bottom, d low, would be, let's see, we'd have 2 times x squared plus 3. And then we'd have to multiply that times the derivative of x squared plus 3, which would be 2x. All over the denominator squared. So x squared plus 3 squared, 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 squared. And I'm just going to clean this up a little bit. I'm going to have, what, negative 12 times x squared plus 3 squared. Plus, because we've got those two negatives, 12 times 2 gives me 24. Oh, you know what? We could actually go ahead and multiply that times 2. Again, that's going to be 48. Scratch that out. 48. X times x gives us x squared. And then we have that times another x squared plus 3. Over the denominator squared is going to be x squared plus 3 to the 4th. Now at this point, notice that we have a factor of x squared plus 3 in all 3 of our terms. So I'm going to go ahead and reduce all of these by a factor of x squared plus 3. If I take out an x squared plus 3 from this term, that's still going to leave me with one of the x squared plus 3's, because right now I've got 2 of them. If I take it out of this term, then that leaves me with 48 x squared. And if I take one of the factors of x squared plus 3 out of the denominator, then I have x squared plus 3 cubed. And I'm just going to go ahead and finish cleaning this up a little bit. Let's see, in the top here, I'd have negative 12x squared minus 36. If I go ahead and distribute the negative 12, plus 48x squared over x squared plus 3 cubed. So then if I do negative 12x squared plus 48x squared, I have 36x squared minus 36 over x squared plus 3 cubed. So that is my second derivative. Oh, that up a little. Okay, so now I have my second derivative. What I need to figure out next is where is my second derivative positive and where is my second derivative negative. And we're going to approach this kind of the same way that we approached finding where our function was increasing and decreasing. We know that we could change signs anytime we go through 0, either by physically crossing 0 and being equal to 0, or by jumping across 0 because we have some point that we're undefined. So what we need to know is where is the second derivative equal to 0 and where is the second derivative undefined or does not exist, because those are the places where the second derivative could change sign. Now this isn't quite finding the critical numbers, because when we say critical numbers, we're saying explicitly that we're talking about the first derivative being 0 or not existing, but it's kind of the same idea. So what we need to know now is where is this second derivative equal to 0 and where is it undefined? Well, in order to be equal to 0, the only way this could be equal to 0 is if the numerator is 0. So I'm going to want to know, where does 36x squared minus 36 equal 0? I could factor out a 36. 36 can't be equal to 0, but x squared minus 1 can equal 0 if x squared equals 1. And that happens when x is plus or minus 1. So we have two places where the derivative, the second derivative is equal to 0. The second derivative would not exist if the denominator, oh, that's cubed. So x squared plus 3 cubed is equal to 0. That happens if x squared plus 3 equals 0, which happens if x squared is equal to negative 3, not negative 3. And if we tried to take the square root of both sides, we would see that there was no real number that would make the denominator equal to 0. So we have two places where the second derivative does not exist. We have one place, or no places, where the second derivative is undefined. So there are two places where the second derivative could change sign. We could change sign at -1. We could also change sign at +1. And what we want to know is, what does the sign of the second derivative look like here, here, and here? If we know that, then we'll know whether or not our graph is concave up or concave down during those intervals. So let's start with a value that's less than -1. Notice that regardless of what value I plug in to the second derivative, whether I plug in a negative value or a positive value or 0 itself, if I square it, if I square the negative value or the positive value, I'm going to get a positive. If I square 0, I'm going to get 0. But then when I add 3, I'm going to have a positive number in either case. So if I have a positive number and I add 3, it's positive. If I have a negative number and I square it and I add 3, it's positive. If I have 0 and I square it and add 3, it's positive. So this part will always be positive. So when I cube it, I'll always get a positive. The denominator here is always going to be positive, which means that whether or not the second derivative is positive or negative will be solely dependent on the numerator. And if we look at the factored form of the numerator, it'll be a little bit easier to figure out. If I take a value that is less than -1 and I square it, it's going to become positive, and it'll be a positive value bigger than 1. So if I subtract 1, I'll have a positive number times 36. So in this region, my second derivative is positive. If I plug in a value in between -1 and 1, like 0, Then I'll have a negative times a positive. So in this region, my second derivative will be negative. And if I plug in a value that's bigger than 1, then when I square it, I get a value bigger than 1. So if I subtract 1, I have a number bigger than 1. So if I multiply it by 36, I'm going to get a positive, which means that in this region, our graph is concave up. Here, we're concave down. And here, we're concave up. So all we have to do is write that interval out and give some justification as to why we know where we are concave up. So we can say that F is concave up, where x is less than -1, and also where x is greater than 1. And we know that because the second derivative is greater than 0 during those regions. We also know that F is concave down between -1 and 1. And we know that because in that region, the second derivative is negative or less than 0. And again, just like when we were discussing intervals of increasing or decreasing, we need to relate that to what information told us that. So just giving the intervals isn't enough. We need to give some kind of justification. So we have to explicitly say, because the second derivative is positive or greater than 0, we know it's concave up. Because the second derivative is negative or less than 0, we know it's concave down.